recording. We're sharing. You guys can see that okay, right? Chapter 4, PowerPoint.
Yeah, I can see it.
All right. Well, you ran through the homework, and I know it's a little weird and confusing. The interesting thing to know, now you got to figure they've been making wires since, the start of the industrial age back in the 1800s, right? I mean, you get down to it, yeah, the machinery's changed and whatnot, become more automated, but things haven't really changed a whole lot. So when they were initially doing this, there we go. So when they were initially doing this, they had you'll find a lot of these sizes and stuff are actually on your drill gauge chart, right? Because they already had these bore sizes laid out. And so they just went ahead and used them. So for certain wire sizes, you won't see an AWG. You'll actually see like some weird bore sizes, which go back to like drill gauge sizes and things like that. Basically, it all comes down to what size the circle is, and all the way up from like super super tiny to super super large. But then they went through and the AWG, the American Wire Gauge, right? They went through and corresponded. But to go back, I mean, these things, as far as like the wire size, they still go back to like an initial bore size. And this was literally, like I say, set in the 1800s. So when you look at a drill gauge chart and stuff, and you try to make heads or tails out of it, yeah, there's a lot of different circular sizes, and that's why we use the mill and whatnot. So, but yeah, most pretty much every wire size you're going to use is going to be specified in the American Wire Gauge. Um, and an interesting thing, right? The higher the AWG number, the smaller the wire size. So if you go and look at a number 30 wire, it's going to be very, very small. And then you go look at like a number 4, the thing is humongous. Um, and one thing to note, now, typically, wires can come in both ways. The very, very small ones are very difficult to have multi-strands. So usually you'll see what they call solid core, right? But stepping up in size, like especially like 12 and 14 and whatnot, those can come in two ways. It could be a solid core where they're just one single strand with inside that insulation, or it could be a multi-strand style. The interesting thing to note, it's just like a little reference, really. There's no major thing with it, but the multi-strand actually has a greater ampacity than the single strand, believe it or not. It is better able to deliver current with the multi-strand than you can with solid core. But that's just one of those little trivia things for you. And another thing to note, after a certain size, you absolutely cannot have solid core. And the reason being is solid core is stiffer, right? So if you get up to a certain size, if you will, and you had a solid core, it would literally be like a copper rod. There would be no way you would be bending this thing. So like it says here, right, see NEC 310.106C, anything over number 8, which is starting to get pretty good size, has to be multi-stranded because you have no pliability. So if you're trying to, bring your wire in and have it go through like a 90-degree bend, yeah, good luck with that. And that would be why. That's the reason why. It's solid core at that point. It's just like a copper rod, and it'd be great for like a grounding purpose or something. But trying to run that through raceways with any kind of bends, 90s or even 45s, good luck. You're not going to do it. So, and again, like with everything, we look at ampacity, and it's always our ability to deliver. And you'll see these ratings on a lot of stuff too. Transformers will have it and whatnot, and you'll always see it specified by, instead of watts, right? Watts is actually the power that is delivered. But for ampacity, you'll typically see it listed as VA, volt amps. And that means that's like the maximum that this particular thing could do. So if you do see that designation of VA, that's what it's talking about relative to like that device or instrument or whatever it is that you're looking at. And we do have a table within the NEC. Tables, there are so many tables and charts in the NEC, it's insane. But this one's one of the more important ones. So Uglies also has it listed off. So you'll be able to reference that up and pull that up and see what your wire ampacity is for specific wire sizes. And that way you could tell, it's like, okay, I need to be able to deliver this current. I need this specific wire size, right? And again, got to look at your environment, right? So temperature, outside factors, even wet, dry, that kind of thing all come into play. But temperatures are important. And why is that? Well, in some ways, as an electrician, the temperature is not your friend, especially as we get hotter. The hotter we get, the less current we can deliver. So what would happen? Well, like let's say you had like a number 14 running through, right? And typically you can expect 15 amps to be able to travel along those wirings. But let's say we're running in an extremely hot environment. What's going to happen is you're not going to be able to deliver that current. It's going to try. It's going to try like hell, okay? But it won't be able to do it. And then what happens is, and this is the bad part, is whatever is driving that current initially will continue to push, higher and higher, trying, it's meant to do it. But so eventually something is going to give out. It'll burn out. You might cause a fire. I mean, there's all types of different things to that. But yeah, temperature is a very big factor, and we always have to look at it. See how it says there, any ambient, outside air type things, right? Greater than 86 degrees. Well, you got to resize your stuff. So if you end up becoming an electrician down in the Southwest, like New Mexico or Arizona or something, you're going to be dealing with some wire size changes, and typically you're going to run larger. So a normal case, like if number 14 was required to, run 15 amps, you might be pulling number 12 instead, just to be able to deliver the amount of current that you want to. Hopefully that makes sense. But they have it all set up for you in the charts. You can look through and see what your temperature is and go ahead and size your wiring accordingly. And of course, it's larger sizes. You're going to be increasing your, prices, right? Larger size wire is going to be a little more expensive. Just something to remember. And so I went over why we do it in mills. And like I say, this goes back quite a long way when, like they say, the Industrial Revolution for the United States, right? Back in the 1800s. That's the way they gauged it. So they're dealing in thousands. So if you were to go into machining or something like that, you would see the same measurement being used. In this case, it would be like bore sizes and drill sizes, right? But we always go back to the circular mills. It's actually used in formulas in conjunction with the kind of wire, like if you're using copper or aluminum, you would actually multiply that into there as well, because copper and aluminum are not the same animal. And we'll show you later with that, with a formula. There's like they call it K for constant. 1K would be for copper would be one number, and then a K for a aluminum would be an entirely different number. But in any case, so, and of course, as always, conductors have to be protected against overcurrent by either a fuse or a circuit breaker, matching your ampacity of that conductor. Because if you go over that, what will end up happening, like let's say you had number 14 running on a 20 amp breaker, and that one day comes when, that thing actually tries to deliver 20 amps, yeah, you're going to make that number 14 start to get really, really hot, and somewhere along the line, it's going to fail. So you always have to match it up for your overcurrent. And these things take a little time to trip. I mean, fuses, you know, it's not like instantaneous, right? Same with circuit breakers. There's literally seconds involved. And I mean, some fuses you can get, they're quicker. And they got ones that are even called like slow blow, which means that they literally take time. And there's a reason why, because whenever you charge something up initially, let's say you just started something, you start a motor, when it first starts up, they have something they call the instantaneous rate of charge. So this thing will literally spike as far as the current goes. It'll spike up and over what it normally would. So let's say you had a 20 amp circuit. Yeah, your initial fire up on a motor or something like that, that's going to take a certain amount of current. It will go up and over the rating, and then it settles, you know, and then it would operate within the normal range. So if we had circuit breakers and fuses meant to instantaneously trip, that's all you'd be doing all day long is go running around and resetting breakers because they'd be tripping all the time. But and these are your typicals. Yeah, of course your load absolutely cannot exceed your branch circuit. Otherwise, you know, you're gonna be tripping the breaker, or in the case that it doesn't do that, you'll be frying some wires out. And a typical for like residential commercial aspect, these are our branch circuit ratings that we deal with. So it's very common that we'll look in and we'll see quite a few 15s and 20s, a few 30s, maybe a couple of 40s, and even a 50 or two. You know, there's as the higher up you go, the less of them you're going to see, right? But you will see these typically in a panel or sub panel, if you will. Okay, let's see here. So when you have like when they call a 20 amp small appliance circuit, right, in a home cannot supply other loads. So typically what that would do is you literally would only have a single wire run just to that specific receptacle or box. You wouldn't have it branching out or anything like that. It would be a single, you know, single run, especially like 30 amps when you have dryers and cooktops. You only have the one receptacle, nothing else would plug into it. Refrigerators, the same thing. You typically don't share receptacle branches with, you know, other things when you have small appliances, because you want to be able to deliver just to that appliance. And 40s and 50s are the big workhorses, right? You might have some like fastened down cooking equipment, you know, the built-in styles where they have like double ovens and that kind of thing going on. So these things are going to draw quite a bit more. And then of course, you have over 50 for the AC and the heating equipment, depending. Of course, you always go back and see what it's rated for, you know, depending on what you have. But it's not uncommon to see that, especially in this day and age. Yeah, and here we go to my favorite one. I truly hate this stuff. So aluminum has less ampacity than copper. And why is that? Well, aluminum has a tendency to get hot faster. And so it starts expanding quicker than copper does. So the same size, they're not rated the same. So be careful when you use aluminum, and you cannot switch and match. I mean, like if you were using receptacles and switches and whatnot that are rated for copper, you absolutely cannot run aluminum conductors to this stuff. And the reason being is aluminum's, you know, it's going to expand. And so when it expands like that, what it'll do is it literally, and this is over time, right? But it will make the screw fasteners eventually start to loosen up, which is a very, very bad thing. So when you're using aluminum, you have to have special rated devices for aluminum. They do have some, I'm not a big fan of these, but they do have some out there that are rated for both that can handle aluminum or copper. But if I were to do it, I mean, just, you know, just as a rule of thumb, aluminum rated devices with aluminum conductors and vice versa, right? Same with copper. You want to keep like with like and no mixing and no matching. And, you know, aluminum has to follow the same rules as copper does, right? We still have to rate the stuff. You can't go over what the conductors are. So you have to look up your tables. So essentially, you're almost doing a whole redo, like if you did aluminum wiring versus copper. And you can expect, based on the way aluminum is, you're going to be running bigger stuff than you normally would with copper. But there was a time there we had the copper shortage and whatnot, and they were really looking at aluminum wiring heavy, and it wasn't uncommon to see this stuff, but it's not as common anymore. But you will run into it occasionally. I don't know. Hopefully not too often. But refer back to your charts, refer back to your tables, make sure you size it accordingly. Yeah, and watch your devices you hook up to this stuff. You gotta, yeah, it takes a little bit longer on the install, right? And then you gotta put this no-lock stuff on there, and that's because of the expansion properties of aluminum. This stuff is nasty, it's goopy, it stinks. It's got a funny smell to it. If you ever run into this stuff, you'll know what I'm talking about. So when you go and put, like wherever you have the connections, or even in a junction box with aluminum, you gotta glop this crap on there, so that way it seals properly. It helps keep the aluminum from like expanding and loosening up the connections and crap like that. But yeah, I hate this stuff. If you ever do run into it, you'll know what I'm talking about. See that tub there? You just so you basically you can even take it and cheat and just dip your, see on the end there, it's actually bare aluminum. It's hard to see, but that is insulation, and then you have the bare aluminum in there. But yeah, you could poke it into the can, if you will. The middle one is actually, when you open that up, you have like a brush, and then the very end one is sort of like an Elmer's glue style one where you can squeeze it and squirt it into the connection areas and stuff. But yeah, I hate this no locks. If you ever run into it, you'll know what I'm talking about. And so now we look at what kind of wire connections we can have. Now, they do use, and this is a weird one, right? See how they have that the crimp type? And when you do use that crimp type, right? Of course, this picture is exposed, but you would have to, you want to take the piss out of this thing, all right? Kind of start at one end, go all the way down, and then back again is a good rule, right? You want to make sure there's nothing exposed. And they'll use this in weird junction areas. Most commonly, why they would do something like this is if you had to bring in another additional wire at a later point in time, or you wanted to make a splice where you ran out of length or something like that, you are allowed to do this. And if you have a good, some good bolt cutters or something, they usually have like a crimp or two on them. Those are always nice to have. So yeah, you just go through and fasten these down, make sure it crimps, and then give it always with any of this stuff, you give it a good tug test, right? So if it comes pulling out of your crimps, and you know that your tug test is has failed. And then the common one that you'll see more often than not, usually like the crimps, and well, I'll get into that in a minute, but more often than not, you'll see these types here, though, the wire connectors. These are the screw-on types, and each color does, in fact, these days, usually on the outside of the container, it'll tell you like how many wires of a certain size, joined together can fit within that style of wire nut. So like the yellows are smaller, the reds are bigger, and so on. So you get varying sizes, but you can only fit so much in. So you always got to take that into account, that you have a good secure connection. And again, once you're done with these, a good rule is tape it. And the reason being is these are twist on, right? So you don't know, you could, let's say you have these in a junction box, but somebody might not go in there for 10 to 20 years or something like that, okay? But there's always, who knows what, house settles, wind, this and that, you get vibrations and whatnot. And over, 10 to 20 years is quite some time. These can eventually back off, where they would slightly untwist, okay? So it's a good rule to go on the very bottom of these things and give it a good, like a loop and a half, loop and a half to 2 loops of electrical tape just to hold it. And what that does is it doesn't insulate it really, but it keeps it from backing off. That way it's going to stay on that connection. Just a little thing. All right, just another one. Hopefully you never really see too many of these. I'm going to be honest, they're a pain in the ass. All right. They're a weird kind of wire nut crimp that you can use to join stuff together, but yeah, you have to have a special tool for these things. They're really difficult. You got to have this thing sized, you got to have your insulated strip then just right and this and that. So I'm not a big fan of those ones. I typically would go like with the top two, very much like in the second one is the most common one you use. Now this other one down here, generally you'll find these on larger wire sizes. And the reason being is, when you screw these down, you want to really mash this down. And they're used more commonly with multi-stranded wire to join together. So what you could do is you could join the 2 posts, right? So let's say you have those like the ones that are displayed with the 2 tabs with the circles in there. You would join those together with a nut and bolt combo, and then you would tape the hell out of it afterwards, okay? But you usually see this in larger sizes. These are the kind that you'll generally find that Ameren and ComEd are doing when they do their cable splicing into the house. This is the type of connection you'll see. And just simply with the nut and bolt style, these things do not come undone, okay? It's a really secure connection. And then the next one, you'll see those from time to time whenever you're required to, to have a tab to lock down. It's a secure way to lock it in. You'll find these sometimes in panels, depending, specialized panels, that kind of thing. It's in one single wire, crimp on. You want to always make sure your crimp is very good. And like I say, give it a good tug test. Grab the end of the tab with your Kleins, your lineman pliers or something like that, and then give it a good pull. If it'll stand a good tug like that, then you've got a good crimp. Otherwise, if it comes undone, then yeah, your crimp wasn't so good. Now, this one, this very last one, I'm not a big fan of these. These are weird. You are allowed to do this. Let's say you're trying to bring in another circuit in the middle of a line somewhere that originally didn't call for it. So what you would do is you would go back to that original wire and literally strip like so much of it so you have it exposed in the middle, and then bring in your new wire in and lock it down with this. And again, once you're done, you gotta tape this thing, and it's quite a few passes. You want to make sure that this thing is taped really, really well, that there's no exposed copper anywhere and that kind of thing. But these are pretty much your most commonly, the ones that you could possibly run into out there. Number 3 is hopefully you never run into, but that's my personal. Excuse me. All righty. So, and again, we go back looking at tables, and even in the uglies chart, this is more of an important one. The types of insulations out there, right? And there's quite a variety. You got MTW, which is motor wire style. You have the THH ones, THHW, THHN, and that's a thermal high. THHN is thermal high nylon. THHW is the same, except it's allowed to be in a wet environment, and so on. You'll find a few, and this way, depending on your situation, you might have some strange circumstance, and you have to match your insulation up for that. Because if you go and try to have this insulation work in an environment that it's not going to, normally meant for, yeah, it'll break down. It'll break down over time. It depends. And then they have a weird, yeah, I mean, our thermoset, right? The THH style. It's the most commonly used ones out there. It's the, the multicolors. It's in Romex. Once you strip back your Romex, the black and white insulation that's on there. You go and it's actually printed on there typically, and you'll be able to read it. And it's like, yeah, TH. So it's a thermal high, and it's the most common. It can handle most temperatures, but again, always match your environment up. If there's something weird, again, like I say, if you're down in Arizona or wiring in the desert for some reason, you might want to match your insulation up, right? Yeah, so you're typically, yeah, wet, damp, dry, and even sunlight. And you got to be careful of like if there's, so odd, but yeah, you might run into a situation where you have some kind of sunlight exposure on your conductor. You got to make sure that it can handle it. Sunlight can do some weird degrading things to nylon over time. We're always looking at a lot of time. I mean, you go in and do a residence and you do a good job without add-ons or something like that, there's more often than not, there's really no reason for some of those boxes to ever come exposed to anything for a good, 10, 20 years and sometimes. But so yeah, again, always match your environment up. If you got a weird situation, look, take some minutes out, look it up in the chart, make sure your installation can match. Otherwise, you got to go and get to the supply store and buy a spool of this stuff. So yeah, we always use is 75 degrees. Well, that's like our typical hottest that we would expect. You always, but again, you got to match your situation. You never know. You're working in some weird area or something, where typically they're going to run a lot hotter. Again, you got to match your formulas up, make sure that these things are not going to exceed this heat. Because you're going to have closed panels, more often time than not, they're going to be like out in the garage or something like that where there is no air conditioning, right? So over the summer, these things can get hot, that kind of thing. So you got to make sure that your stuff matches up with this. And you even got to figure that running through the house, right? There are generally a lot of times, exterior walls, up in crawl spaces. Again, there's no air conditioning. There's no heat typically to these areas. So your wire is going to get exposed to, quite a range of temperatures over time. So you got to make sure you're matched up right for your environment. They even go through, depending on the area of the United States you live in, I generally plan that, or even around the world. You never know if you end up wiring in Saudi Arabia or something. They generally have it zoned out like what your typical temperatures are going to be. So you can kind of match your wiring up to that zone. So you would kind of look, okay, I'm wiring here. What's my zone? And what am I looking at as my average temperature? So you can look that up as well. They've got charts for all this stuff. And over time, like let's say you're always in Illinois, so you're always wiring in Illinois, you come to generally know what your temperature requirements are going to be on the average, right? And even recognize when I'm going to have like a weird scenario, because you always run into weird scenarios. But yeah, the weakest link is always the one with the lowest rating. That's the one that could break down, right? So through your whole run, whatever is the lowest one, that's your weakest link. And that would be the one you would have to worry about. So you always want to make sure that you don't have that weakest link, that it's matched up good. So yeah, and that's funny because I actually had in my locker back at school, I do have an old knob and tube set that was pulled out of a house that I could show you guys what this stuff looked like. They use like a cloth asbestos style insulation around it, right? And the knob and tube, they literally had God, you can still find pictures of this stuff, but it was like a ceramic post, okay? And if you ever look back at the old pictures, they didn't have like a whole lot of anything like junction boxes. So what they would do is have these ceramic posts that would be shared. And then out on the end of this stuff, it would literally be stripped and exposed. So up in your crawl spaces, in your basements or whatnot, you would have this exposed wiring running around, and it was crazy. And then they wondered why they had fires, creating potential fire hazards. These things, and then the insulation even over time, because it was that cloth weave, Yeah, I've had many a time, especially when I was in Chicago, we'd run into like some of these old apartment buildings, right? You start monkeying around with some of this stuff, and I swear to God, this insulation was so brittle. The minute you started even doing anything, the crap would just crumble and start falling apart, and you'd be like, "Oh, Jesus!" And you had to be careful because you didn't want it crumbling too far back. And then a lot of what they did too, because they had because back in the day, some of these really old apartment buildings literally had gas pipes running. So they had like they had, before electricity, they literally had like gas lights running in the house. So these pipes would still be in the walls, and then later when they switched, believe it or not, there was a certain amount of these gas pipes that they reused, and then they ran this crappy crappy asbestos insulated wiring through it. So you'd get some strange, really strange configurations that you would run into, and the pipe looked all weird, because it was the old, the black style pipe and whatnot. But yeah, you run into some things. Yeah, here you go. So yeah, look at this crap. So see those ceramic posts? I mean, granted, they're covered, if you will, but that literally that little divide in there is exposed. That's exposed wiring. So like little mice or crap over time, anything comes up in there, it would create definite like wire hazard, fire hazard. Stuff was awful. Hopefully you never. Oh, there's still some farmhouses out there with this. Believe it or not, with this crap still running through it. All right. Now we come to something a little more specific to residential and commercial aspects, where we get a neutral. And the neutrals, that comes out from the transformer out in the pole or underground, whatever case you got. But it comes from the transformer, and what they do is a center tap on that bad boy. So you'll have two hot lines coming into your house, okay, both from the outer ends of the transformer. Each one's 120, and then going back to that center tap of the to the transformer. So it's 120 and 120, two main feeds, right? Well, they pull three wires into your house. So two of them are hot, and then one is the neutral. And the neutral basically lets the current travel, because you have to have a return path, right? So you get the current coming in, you got to have current going back out. And the neutral rides the current back out to the transformer. And so you'll run it through the house. In residential, it's white. In commercial, more often than not, it should also be white, the black, red, and white. Um, when you get into industrial settings, that changes, but we're not going to cover that really. But yeah, it doesn't. The neutral is more often than not going to carry the heavy current loads, because usually the hot will deliver through the receptacles and the lighting and whatnot, and the current's being used by a device, right? But you have to have a current traveling path to go back, right? But more often than not, you're not going to have too much current going back on the neutral. And if you have no devices at all hooked up and everything's wired correctly, your neutral really shouldn't have anything on it. But you always got to take that with a grain of salt, that the electrician before you knew what he was doing. You get people out there wiring stuff that shouldn't be, but um, but yeah, you can have the neutral conductor be on a smaller gauge than the hot. Rule of thumb is usually, you pull them wire through, and you got like number 14 traveling through a branch. Your neutral is going to be number 14 as well, but it's not unheard of that it could be like a number 16 or something like that. So if you do see it be a little smaller than what the hot is, that's not allowed, I guess you should say. But the NEC does have specifics. You have to be careful, right? Continuous duty, that kind of thing. You're generally not allowed to undersize, but for certain situations you could. And so here's what I was talking about, basically. So here you got two hots, right? Phase A and phase B. Like I say, black, red, and white. So on the one side, commonly it's just you're using one leg or the other leg, typically. And there are cases where you have some devices that'll be pulling both, right? That'll usually be on the heavy duty stuff, continuous duty type things where air conditioning or the furnace or something like that, motors are usually involved. And you'll run two phases into it, and they call that 240. And in that case, you wouldn't see the neutral there for that, okay? But that's allowable because that runs on both sides of the transformer, so the current path is allowed to, delivered back. But for most devices to your house, you're usually running the black and white or the red and white. You have both legs in the panel, and that's how you look in the panel. You'll see two sides to it typically, right? So on one side is where phase A, and then on the other side of the, where the circuit breakers are all populated, that would be phase B. And it's usually an even distribution throughout the house, which you'll see later when we get more into it. But this is pretty much how they bring it in, and what you can pretty much expect to see. Now we're going to get into something, and this is a very common thing. It's basically over any given length of a wire run, you have something they call the voltage drop. It's not significant. You're not like losing power immediately, but over a certain amount of time, if you do have like an extremely long run, yeah, you can expect there to be a certain amount. So if you were running something and you had to have, you need the 110 down in the end, but let's say it's such a length that really you fell under it and you're delivering like 105, yeah, that's not going to work. Because they have a thing, there's an organization out there when they started doing like appliances and whatnot, it's called NEMA, and that's the Equipment Manufacturers Association, okay? And a long time ago, because initially voltage was crazy. There could be all kinds of different voltage ranges and stuff like that into a house. You could have 97 volts in your house or something crazy, and it would depend on the power, your local power company and that kind of thing. But NEMA came in and through, because they started doing appliances, and they wanted to be able to, crank out radios and washers and dryers across the whole country. But you didn't want to make, a different one for each area kind of thing. That would be nuts, right? So NEMA went through and they specified, it's like, well, you're only allowed to run this range, and that's pretty much it. So NEMA is the one that specifies the range, and then we have to stick to that. Excuse me. So when you do your wire runs, you have to be careful, because if it's too long of a run, your voltage is going to fall too far down and it's not going to work. So whatever you're running to, somebody goes and plugs a device in and it's like 97 volts and it's meant to run with 110. Well, it might sort of work, but it might sort of not. So we do have a calculation for this, right? And so it depends on how long the run is. So anything over this run, what would happen is, okay, so let's say, like in this example, you had a 30 amp load and you're going to be 330 feet. And typically for a 30 amp load, right, you'd use number 10, okay? But let's say it fell too far down, and what would happen is if you drop down underneath it, what you would have to do is go to the next size up. And so instead of number 10, what you would have to do if it didn't meet what you needed it to be, you would end up running number 8 because it would have the greater ampacity, right? The greater VA. So then it would be able to deliver, and then it wouldn't fall under the rating it needed to be. So always take this into mind when you do have like a really long run. I don't know, who knows? You never know what somebody's houses are shaped so weird, and you might have a really long wire run or something. You would have to resize it and stuff like that. And you could check it. That's why you got your meter. Your meter is your number one friend. You always have them. But you can even check that, like, let's say somebody had done work previously and didn't do the voltage drop formula, and the customer's calling up and saying, hey, I've got too little voltage. Well, you go out there, your voltmeter, take a read on it and go, oh, yeah, you're right. But you can even see in this example, it's like, okay, so at the beginning of the run, you see that voltmeter's reading 120 volts, right? But at the end of the run, we literally lost 3.6 volts, which is totally doable, you know. But that's why when you go through a house and you look, like, let's say we look back at the panel, oh yeah, I got 120 here, but then you go start looking in the house and you see like 118 and 117 and so on. That's what's going on. You're literally having a voltage drop going on. And as long as it's, like I say, as long as it's within the, the doable range, you're fine. But again, if you do your formula and it doesn't come out right, yep, next wire size up is what you got to do. So we look and we see, yeah, what's our, what we're allowed, and how much we can, we can't exceed past that point, basically. And again, your voltmeter's your friend. And in this case, you got like a sub panel, and where you would see something like that is where like your AC condenser that's outside, right? So you have a main circuit breaker back in the panel for the AC, but then it's got a feed out to, I don't know, wherever in the back of the house, the side of the house, or whatnot. You'll have a sub panel located there, and that could have circuit breakers or it could have fuses in there, but it's got to be a type of because you have to be able to see your disconnect typically when you're doing something like that, right? So in the case of the AC, if the circuit breaker's inside of the house, or even in the garage, and you're in the back of the house, you can't see if somebody else is going to come along and flip the switch, right? So what they do is, this is a safety thing. So usually you'll have a sub panel for disconnect, so you control when you're working on it, right? We never, ever work on live stuff. Hope it's going okay. I mean, I know it's a lot of dry stuff out there. Nothing like talking about wiring and wiring sizes, but now we get into my most favorite wiring, non-metallic sheet. Why do they call it non-metallic? Well, because it's not running in a conduit, okay? And the outside of it is like a nylon type of insulation. And inside you'll generally find, at the minimum, you'll find about 3 wires, because you got 1 hot, 1 neutral, and 1 ground. And it could be more than that. You could have, oh God, there's so many flavors of it. It's crazy. But yeah, it's non-metallic sheet that we almost everybody calls Romex. But I guess technically it's incorrect, because Romex is actually a brand. And there are other manufacturers out there. So the specific technical term for Romex is non-metallic sheet cable. And like I say, the minimal is you're going to have 3 conductors in that bad boy: hot, neutral, and a ground. And you can find this in the NEC, right? Article 334. And they even have specific styles of connectors. You wouldn't use an EMT connector on a non-metallic sheet, because it would just be too big. You would never be able to lock it down. And again, remember, strain relief. You cannot be able to tug those cables like in a box, in a panel, or something like that. They have to be securely fastened. So you'll look at these styles, right? We got these connectors. There's a 90 there, and a straight. Your sheet basically goes through these things and clamps down on it. And then on the other side, when it comes in the panel, notice, right, nice and clean. You really have minimal amount of sheathing, so you want to basically peel that sheathing back all the way to pretty much the edge of that connector if you can, or as close to it as you can. And then, of course, keeping it on the outside. And yeah, you can run into different ones. They even have so many weird looking ones, but these are the typicals. You get a straight feed through one, or you get the little weird, the 90s. And the 90s, you feed that sheet through there, and then that style, what it does is sort of like a flange. It'll clamp down on the sheet. And again, when you do these things, it's a good idea. Always give your stuff a tug test. Can't pass a tug test, and it's no good. You gotta find a different thing, because these things are size specific, right? So you always got to match up. Like, okay, so like I said earlier, your number 14 sheet cable is, of course, going to be a different size than your number 12 sheet cable. Okay, so you have to match up your connectors and couplings and stuff like that to make sure that it's the right size for that. And they have it always printed, you know, you get the box of these, you know, 5/8, 3/8, and that kind of thing. And just make sure you got the right sizes for your stuff. If you don't, then it's not going to work, and you would never pass like an actual inspection because you wouldn't be able to pass the strain relief test. All righty. So in chapter 3, they talk about a whole bunch of stuff, and the reason I do like that book is they do a lot of NEC references, and he shows you, you know, I like the pictures in there. You good examples of, you know, showing you the proper way to do stuff. I mean, if you keep this book with you, I even still refer to it sometimes, you know, if I'm doing monkeying around in the house or something, I'll look back, it's like, yeah, you know, I haven't done that in a while. I better double check, that kind of thing. But and plus I think it's a little easier to read, you know, because it's interpreting the NEC already for you. And like I say, you know, I always say the NEC is like what do you call it, legal speak. And sometimes legal speak is so insane to read, you know, the lawyers speak stuff. But with the textbook, at least it does a pretty decent job of explaining it to you. But yeah, we can go back and look if we wanted to. We can look at the NEC under Article 334, right, and see what our rules are for this kind of thing. And I think if you guys went through that article that I had you go through, you can see that what would happen in a case where the electrician wasn't taking precautions with his sheath cable. And that's the drawback with that stuff, you know. Like I say, if you're running it in conduit, you typically don't have to worry about, you know, nails or screws coming into the wall and hitting into stuff. But when you run the sheath cable, you got to really think about, you know, where it's being routed, because at some point, you know, even if it's hanging a picture on the wall or something like that, people are going to be driving nails through the walls. It's to be expected. But we have some specifics, right? How much, and the reason with the straps or the staples on there is the amount of sag, because if we go too far, it's allowed to sag, and it almost like be like a grab point too, right? So again, we're looking at the strain relief. You want to keep the sag out of the cable if at all possible, because if it does sag too much over time, you know, if it's settled, it might travel somewhere where you didn't plan on it to, and here we come with the nails and screws, because you never know. But there's specifics with this, and we want to follow those. Make sure we follow a good run, keep it secured, and that's why this stuff is a real pain in the butt. If you're coming in like way later, let's say you already have a finished house, right, and you're trying to reroute something in. Let's say you're bringing it in through the crawl space upstairs or something. It's going to be very difficult for you once you get into the wall to mount it to anything, but you got to make sure that you're really trying to follow the rules. You know, and people, excuse me, you're not going to be too often like tearing open their walls just to be able to securely fasten this stuff. But always remember, just keep things aware, right? And then there's ways to fasten for wood versus metal. You won't see, sometimes you will, but too often in residential, I would expect more like metal studs to be used in commercial. And it's just because of the anti-fire thing. But the good thing about metal studs too, yeah, you can't get them eaten by termites, but they're a pain in the butt to deal with on occasion when you try to route stuff through, because trying to drill holes in that metal crap is a pain in the butt sometimes, whereas the wood is a lot easier. But yeah, you always want to try to drill out your holes in the center. And we do have little plate covers that can be inserted in there to protect your sheath cabling once it's installed. Yeah, see there? Get the little nail blockers. And so basically you have to apply those and put them up over. Basically that way, whenever anybody drives a nail or a screw into the wall at that point, it's going to bounce off or skip off. Yeah, basically they shouldn't be able to drive it through. But some people are determined sometimes. You got to be, so you want to use the right ones, make sure that they got the right thickness, you know, because people will try, believe it or not. It's kind of crazy. But you gotta protect them from themselves. That's part of our job. So, and these have good examples. You can go back and look through here, but the book lays these out for you. but yeah, the NEC does specify it's got to be a certain thickness to it. And it's just to be able to stand up to, like, drywall screws and nails and that type of thing. Because you go too thin, and eventually somebody, especially if they use like a power drill, they might be able to punch through it. So you want to make sure the steel plate's a nice thick one. And the places to be careful sometimes, especially shallow grooves when you have to route it through an area where you're not going to be able to have, be able to put any protection on it or something like that. You got to watch how you're routing it through that groove. Make sure it's somewhere where, it's not accessible from the outside type of thing. And then if you're running through chases, again, you have to have the steel plate blocking over it, that kind of thing. And chases are weird. You might get those sometimes, with like concrete type things or situations where you have to route it through that area. But always watch, and then with these guys, why would you have to have a little nylon plug like that, right? And the reason being is because if you have the metal, you're going to have the sheath cable sitting on those edges. And over time, vibration and whatnot, your sheath cable it'll start to slice. So these little nylon grommets or bushings, you basically insert them in, and they even have like a little fastener thing. If you look on the side there, it almost looks like the little two-way tabs, and then it would have a ring, and so the ring on the other side would just basically secure it and hold it on. And that way your cable's protected from slicing through the 2x4 over time. It does happen. Yeah, rules with these things, right? You got to watch what you're running it. You're typically not allowed to run up and over like joists or 2x4s. You got to run through, and then go ahead and protect it on the through. But you would be amazed. I'm sure you're going to run into times where you literally will see that Romex riding the waves up on the top in a crawl space, like up over the tops of all the joists, And you don't want that, because if people come up there and work or whatnot, they're going to be stepping on your wiring and all kinds of crap. But the things you'll see. And then they have rules on ducting, that type of thing. You have to be careful when wiring it, because ducts, again, are metal. And so basically you have to be make sure that at no point are you going to have a situation where you end up energizing the ductway, and we're talking like AC heating ducts and that type of thing. So if you do have to fasten onto the ductwork, you have to follow some rules just to be sure that there's no way that you're going to end up energizing the ductway at all. So again, securely fasten. You got to watch how you're routing. Certain you're allowed certain runs, if you will. When I think free hanging or too much sag, because if it has too much sag, it's like a grapple point, that type of thing. Because see how they got it routed through, like going through the joists and the holes there. Yeah, that would be, you'd have to watch that, because again, you want to pull it tight, taut, and following through. Yeah, running boards, you got to be careful of that. Because again, if it's like a step point, that type of thing, you got to be, people will step on this stuff. If it's there to be stepped on at one point in time, I guarantee you somebody is going to step on it. So watch your ride. So yeah, in this day and age, you get lucky. Like even I've seen even some, they got like some weird tabs with the metal boxes now, where it's got like a sort of a built-in clamp, kind of, if you will, where you can literally, instead of punching a knockout and adding a separate connector, it literally has a clamp for the sheath cable already built into it. And then all you have to do is basically screw it down, to fasten it down. The nylon ones, the blue plastic ones, typically, they've got a tab in the back where once you push the sheath through, this thing has like a certain amount of tension on it where it'll pass a good tug test with no problem. Just be careful when you're doing those. Those things are tight. So if you end up pushing on it too hard and stuff, you know, this rare situation, but it can happen, and you can end up breaking that damn tab, and then of course now you got to go get a new box, which is one of those fun runs, you know, especially if you have only specific equipment, you don't have extras. Yeah, your butt's going back to the hardware or supply store and getting another one. But they'll tell you to, and it's, you know, and typically, right, you got one connector, you have one cable. Because if you have two cables into one connector, you know, you're trying to clamp down, it will not pass the tug test because you won't have enough tension on both sides of that cabling or wiring, if you will. There are some weird, these are rare though, but there are some weird cable connectors that you can have more than one running through it. But like it says on that bottom point there, you have to make sure that it does say, yes, allow more, you know, more than one cable. It says acceptable for two cables or something like that on there. If not, it's one per connector. That is a rule. And then we get into, and this, I mean, it depends. You might run into situations where the residential homeowner wanted you to run conduit, which if you're not used to dealing with on a regular basis is a lot of fun because now you got to go and make all these bends and stuff that you're not used to doing. But, and there's commercial situations, definitely, and always, always, always in industrial settings. Everything, in fact, you will not see sheet non-metallic cable used in an industrial setting. I'm pretty sure it's not allowed. But yeah, it's typically what you'll see it referred to as EMT, right? Conduit. It's electrical metallic tubing, and they come in different sizes. The most commons are half inch and 3/4. The cool thing is they've got tables and charts, and it's actually right in your uglies book too, on how many conductors can go through these things. So you got to remember that, and don't try to overstuff, you know, a conduit. One, it'll be a royal pain in the butt trying to pull wire through those things. Okay, and two, if you have heat buildup and this thing is crammed, yeah, what'll happen is that the copper will expand and it'll literally degrade your insulation. So, but Yuggly's book, and like I say, the NEC definitely has some real good tables and charts, and it says, you know, so if you have like half-inch conduit and you're dealing with number 14 wire, how many number 14 conductors can you get through a half-inch conduit? And it tells you exactly. And then it even there's a formula that we can use for you know, tubings and raceways and even boxes where, you know, because you're going to get situations where you mix and match where you might have number 12 and number 14 both going through this tubing or raceways or whatnot. So you can go ahead and actually calculate through and figure out, okay, I'm allowed this much and this much, and that's how much we can push through here. But you always refer back to it, unless you're, you know, literally, unless you are literally doing this on like a very, very daily basis, you're not going to know how many conductors are going to go through that pipe. I don't care if you're a journeyman or whatever. You're going to be looking back. You're going to be looking back at these tables and charts and going, okay, that's how many we do. You know, that type of thing. And then we run into this stuff, flex. You run into it from time to time, and there's a couple of varieties out there. You got the straight flex metallic on the outside. They got a flex where it's actually like a nylon style, if you will, you know, sort of a PVC style. And then you have the flex like you see in the bottom with the air conditioner. It has like an outer insulated nylon coating to it, which is meant to handle, you know, outdoor extremes, that kind of thing. And you would run your wiring through that. But yeah, you'll run into a variety of these things, and you got to be careful. You're only allowed about, I'm pretty sure, a 36-inch run maximum of this stuff by code. And then you got to make sure, you know, it's the right, again, right sizing for the amount of conductors you have through it. And they even have the type, you can buy this stuff already stuffed with wiring. And if you have a lot of bends that are going to happen with this stuff, you know, or it's going to be because it's flexible. So trying to pull wire through it can be a royal pain in the butt. I'm not going to lie. So there might be situations where you have to run out there and yeah, actually have it already populated and just go ahead and run that through. You'll save yourself a ton of headaches. But yeah, you'll run through stuff. And here we go with the non-metallic style, right? The PVC style. You got to be careful with this stuff. It can be in the right kind of temperatures, real brittle, you know, when it's cold outside and stuff like that. And if you try to overflex it when it's brittle like that, yeah, you can end up cracking it, in which case now it's junk and you're gonna have to start all over again, right? And they have special connectors, always match up, you know. If you're using the PVC style, you got to have the PVC connectors. You're using the metallic, use metallic connectors. If you're using the insulated variety, they actually have special, I've seen this, people will literally use insulated all the way through the run, right? And then use a damn non-insulated connector to join it through. And it's like, what the hell was the point of that then? So they make special insulated style. It's like a compression fitting, right? Because you want to, if you're running this stuff already, you want to keep moisture out, obviously. So go ahead and using a non-sealed connector on the end. You might as well just not have run the crap. So make sure you match up the right connectors to the right kind of tubing when you use this stuff, okay? Yeah, Smurf tube because of the blue. But yeah, you'll run into a variety of this stuff out there. Kind of cool. And I have an exercise that would be going through and doing a couple of calculations, right? We're service entrance. So how do you calculate what your service entrance or what your utility drop is supposed to be? Because you know you're not going to run, let's say you had a 100, you don't see, well, you still will see 60 amp services out there. You just won't see any new 60 amp services out there. I think a 100 amp is the minimum, and even that is starting to actually phase out nowadays. They actually even go up to so crazy, it's a 400 amp service where it's like a double pull to a house. So you literally have two different 200 amp panels like in your garage or wherever, because the power requirements and stuff of houses with all our toys and stuff is going up. But yeah, you still see some people pull a 100 amp, but if you're getting a brand new house, what would be the point? I would go with a 200 amp service. But depending on your service, that's that's going to dictate what your wire size is, right? Because you can always go up larger, but you got to remember, unless you're the one paying the bill, your customer generally doesn't want to pay extra for stuff if he doesn't have to, right? You want to keep your costs down. So match, this is why we go through and match wiring sizes. And again, you can always go larger, but there's going to be extra cost for that stuff. So we try to match up. We do like a service entrance calculations and size up the wire to depending on the service, right? Like I say, 100 amp, 200 amp, and so on. And we're going to match up that specific wire size and what we're going to use. And of course, how long your run is. So that also includes the voltage drop calculation. Because if you're like gazillion miles away from your transformer, well, you're going up in wire size because of that. And that, my friends, is pretty much my lecture for today. And I've got one other thing, and this is a sad point for me. Something called pigtails when we do boxes, okay? So, and you'll, so horrible. I hate non-electricians that do electrical work, but you'll see it from time to time in like junction boxes, or well, primarily like in connections, like in what do I want? Like just receptacles and switches. So let's say you have a couple wires coming in, okay? You're gonna join them together and have like a wire nut or whatnot on it, okay? But now some people will go through and literally use like the receptacle as the junction, right? So they'll have these couple of wires hooked up to it, and it's like, no, 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 no. So a pigtail, what that is, I don't know if I have a good picture. No, I don't. What a pigtail would do is you would literally go from that connection, you would run an extra wire about 6 inches, right? You don't want to go too large because then it counts as 2 conductors in the box. So you got to be careful of that, but typically about 6 inches. And so what you would do is, like, if you had a multi-strand thing coming in, you would run a pigtail out both on the hot and the neutral side, and you run it to the device. And the reason being, there's a couple of reasons. Let's say you have a point where you have to disconnect or something like that, or the device fails. It could literally, if the device failed and you're using it as like a junction wave, right? What happens on the further leg is you all of a sudden have no power on that end. So with the pigtail, everything else that's dependent doesn't rely on that device is really what they're going for. You never want to be device dependent on a branch run, because you're feeding multiple receptacles or multiple lights or that kind of thing. So you never typically wire directly. What you'll do is, in a case where you have a couple of wires and that kind of thing, you typically run a pigtail out so things further down the line are not interrupted by a device failure. And of course, usually in the lab, I give a little demonstration on what the pigtail should look like, but I don't have that today. But I'm going to go through and get some pictures posted up too, some further stuff so we can all take a look. Stop sharing that there. So you guys doing good with everything so far? Or is this, I mean, like I say, it's like I expect about 2 chapters a week from me. I'm gonna be good on my promise for that. But the homework seemed like it's too much for you, or?
That's fine.
Yeah, it's a lot.
I wish there's a chapter 27 homework, chapter 20 homework. There's no, you haven't put chapter 27, 28 on Blackboard yet.
Wait, what was that?
The next homework to do is chapter 27, 28. Over the
27 and 29, isn't it? Double check here.
It's 27, 28.
We look for today. Yeah, because your homework assignment, read chapters 27 and 29. You get assigned chapter 27 today. Check my calendar.
It says 28 on Monday, or for Monday.
Oh, yeah, you're right. I did put the wrong one in there, didn't I? How about that?
But those chapters aren't under the course.
Oh, for the
they're not under textbook yet. The textbook and course content yet.
You're right. All right, I'm gonna have to go through that after we're done here, Jared. Go through here. And then I have to post them up for our electronic book too, don't I? What do I got for textbook? Yeah, I just go up to 21. Okay. Yeah, because after that I got separate chapters, so I'll go through and make sure I post them all. The drawings are all in there. The uglies book's on there, but yeah, I forgot. Okay. Yeah, I'll go through today and I'll correct all that. Well, our main course today is just chapter 27 is what we're going to jump to. And then when we get through these 2 chapters, then we'll jump back and go to chapter 5 and 6, I believe. We just had to take a look at, because we want to look at some of the, the service entrance stuff. I also have there's like a voltage drop exercise I have on there I posted. So I got like 3 things today, if you can go through them. And usually that minimum lighting circuits thing was a lab. Hold on here. But I'm gonna post it as an exercise, I guess.
The voltage drop thing isn't the thing saying it's a homework.
There, see that? I got the voltage drop exercise, your minimum lighting circuits, and then the homework. And you're right.
Blackboard says that the voltage drop exercise isn't homework.
Finding it as homework.
The course calendar is There's nothing on the course calendar. There's just ultra exercise.
You don't have anything?
All this is for Friday. It doesn't show voltage drop exercise. It shows the other two things. It shows chapter 27, the lighting thing, but it doesn't show the voltage drop.
Okay, hold on. Well, let's take a look at why. Make available. A couple of tabs. Display. Due date. That's really weird. I wonder what. Should be coming. Still nothing?
Also, it's just not showing up. Of course, on the course calendar.
Yeah, see, it shows up on mine. Due date 4/17. What the hell? Sometimes I hate Blackboard. I really do. Oh, didn't want that. Hold on. Hold on. Let me make unavailable. Make available. Let's see if that works. Everything on here says it should be there. Make available to students. Temps. Latest grade. Well, how about tell it to display? Just to be on the safe side here. No password. Due date. Submit. Still not. But does it show up under your day 5 tab?
It's on a day 5 tab. I still do it just on the calendar.
Okay. I have no idea why that is. Everything I have checked is just like everything else. Because I had a problem with that other one was like that too, and I don't know why. I don't know why. It's like one of those weird, strange things. Yeah, I'll have to go through and fix that as well. It's chapter 27. All right. Because let me see. Then we go. Oh no. That's chapter 28. Oh, I must have bounced it around somehow. Oh, well, I did that. Huh. All right. Well, I'll have to go through and fix that part. Yeah, it's really weird.
You're done.
Yeah, we're done. I'll make sure we fix it. But yeah, our focus from today is we're going to go into chapter 27 and then check out the homework for that. I got a couple, like I said, a couple exercises for today. And there's even an example of the temperature adjustment chart from NEC there for you if you want to refer back to that. Otherwise, the Uglies book has that in there too. You know, this is a straight copy of NEC's as far as like your temperature adjustment. But yeah, if you guys are doing good and we don't have any questions, I am good. Stop her there. Hope everybody's doing okay out there. But all right,
Mm,
you gentlemen are all good. No questions. We're all
Nope.
okay. Well, if you have anything, just like I say, go ahead and email me or text me. I'm usually pretty open, so any which way you need to do it and get a hold of me, and I'll do my best to help you out any way I can.
Fine.
All righty.
Yep.
Have a good one, Joseph.
Yep. You too.